Hi everyone. Today we are looking at an important topic in 5G NR, which is the difference between antenna ports, layers, ranks, and the entire RAN signal processing chain. Many times you might have stared at a 5G protocol trace and wondered why there are so many terms for seemingly similar concepts. At least that was my first thought as a RAN engineer when I began learning this stuff. Um, why can't we just send data from antennas? Why do we need all these abstractions? How does physical antenna ports differ from logical antenna ports, and how different are layers to ranks? So this video basically intends to clarify all these concepts for you. So this video aims to explain how these concepts relates to each other, and it aims to explain it in such a way that you, the next time when you see this term, you should intuitively know that okay, this is what's meant by logical antenna ports, this is what's meant by layers. Without much further ado, let's proceed to the basic RAN signal processing chain. So the fundamental entity in the RAN signal processing is the transport block. The transport block is the data that is sent by the MAC layer to the physical layer over transport channel. The transport block then undergoes further processing to become a code word at the physical layer, and this is transmitted over layers to the logical antenna ports, from where it is mapped to the physical antenna and then transmitted over the RAN air interface. So please keep in mind that in this video we are explaining from a RAN perspective because I am a RAN engineer, and so for most of the 3GPP specs are written from a UE perspective. So I guess this would be a fresh perspective for you if you are a UE engineer. But anyways, let's move on to the video. To get an intuitive explanation of this RAN signal processing chain, let us think of this as a factory assembly line. So each stage does one specific job. So think of the transport block here as the raw package that needs to be sent over the over the channel or over the belts in a factory, and then this raw package gets added a label, a destination and center address, and then it is packaged to a code word. Then these packages have to be transmitted to their respective destination addresses or to the respective loading docks, where trucks are waiting for them. So these layers actually correspond to the active conveyor belts in that factory. These code words, these transport blocks which are packaged in code words, are transmitted over multiple layers and to their destination. And precoding is basically the control logic, the control algorithm that guides which layer should go to which destination. And then we have these logical antenna ports, which are basically the truck loading, the loading docks for the packages, and where the packages get loaded onto the trucks. And then these physical antennas are actually the transport medium which transports these packages. Yeah, that was kind of an intuitive explanation for each of these blocks in this diagram. So here, take care that all the steps still logical antenna ports. These are all specified by 3GPP. So the UE knows only till logical antenna ports. So the rest of these analog beamforming and physical antennas are vendor specific. The UE doesn't know actually how many physical antennas there are at a G node B. And the UE only knows that okay, there are a certain number of logical antenna ports at the G node B. Okay, now let us look at the first block in this RAN processing chain. So the transport block is the output of the MAC layer processing. This is handed over to the physical layer. So in our factory line assembly, this transport block is the raw package to the ship. So it has no label attached to it, so a delivery guy looking at this package has no idea where it should go. So every RAN engineer should know that one transport block is generated per TTI or per transmission time interval. So in 5G, a typical TTI duration is like around 1 millisecond approximately. This is 1 millisecond in 15 kilohertz, which is like one slot. The size of this transport block is actually not fixed. So the transport block size actually depends upon the MCS, the modulation and coding scheme, then the number of PRBs, the number of physical resource blocks, and then the number of layers or rank of the channel. And thus the size of the transport block can range from a few bytes to like around 1.2 megabits per second. Now, the transport block, once it arrives at the physical layer, undergoes a series of processing. So, firstly, the physical layer adds a CRC attachment to it. So, CRC stands for cyclic redundancy code check, and then it adds this cyclic redundancy code check to verify if there are any errors in the transport block while it is transmitted over the air interface. Afterwards, an LDPC encoding is added. This is so that the UE can correct any errors. The next step is to match the rate. So this adjusts the number of coded bits to fit the allocated resources. Afterwards, scrambling is done to prevent intercell interference patterns. The final step in this processing chain is to modulate the transport block onto complex symbols. So finally, after all these steps are applied, a transport block becomes a code word. So this is the physical layer entity. The physical layer does not know about the transport block. The physical layer does after further processing on code words. Now, so a code word is thus a fully encoded and modulated version of a transport block. It's the output of the channel coding that is applied to a transport block. Now the transport block is ready to be placed on a resource grid. So each code word thus has its own modulation and coding scheme. Since each transport block is associated with its own HARQ ID, each code word has its HARQ process also. Now for ranks 1 to 4, per TTI, one transport block is generated, whereas for ranks 5 to 8 per TTI, there are like around 2 transport blocks that are generated. Thus, 2 code words are also generated. So, when you're looking at a trace and see 2 code words, just think that okay, the channel rank could be 5 or above. Now, let us look at another quite important topic in 5G NR, which is layers versus ranks. So layer and rank are two concepts that are closely related. So layer represents the actual number of transmission channels that are generated, while rank is the property of the channel. So a layer represents the number of spatial streams that the G node B decides to transmit in a given PDSH, for example. So on the other hand, rank actually represents the ability of the channel to support these layers. In our factory analogy, think of layers as the conveyor belts that are in operation. So ranks represents the total number of conveyor belts that are available. Out of this, some may be in function, some may not be in function. Think of layers as the one that are in function. So layers, the number of layers has to be always less than the rank of the channel. And this again, the rank of the channel, this again depends upon the number of transmit and receive ports of the G node B. Why do we need layers? So again, in our factory analogy, think as the number of conveyor belts increases, more and more transport blocks, more and more code words can be transmitted onto the destination. So this increases the throughput of the G node B. So layers are a logical concept. They don't correspond to specific antennas yet. Let us look at a layer mapping example. So um, we have a code word with a couple of symbols. We have S0, S1, S2, S3, and S4. Think of a think of a channel with rank 4 or layer 4. Usually when we say rank 4 in GNODB, we usually means layer because number of layers equal to number of rank of a channel usually. I mean, we are speaking about a general case here, and for mapping these code words into layer, typically a round robin pattern is used, such that code word S0 and S4 would be mapped to layer 0, then S1 and S5 would be mapped to layer 1, and so on and so forth. So this is basically a round robin distribution. Now let us look at the next important step in the RAN processing chain, which is precoding. So precoding takes the layer signals. It takes the layer signals and maps them to a logical. It takes the layers and map them to a logical antenna ports. So it uses matrix multiplication and for this mapping. So think of precoding as routing each conveyor belt to the correct loading dock. So this figure actually shows how this precoding operation would work on a two-layer transmission. So here the total number of output logical ports is 4. The rank of the channel or totally 2 layers are used, and this is this precoding matrix that is used uh, um, for multiplication. So this every logical port that is outputted, it carries a weighted combination of all the layers on which code words are also mapped. Here the size of this precoder matrix is 4 by 2. The size of this layer matrix is 2 by 1, and hence the output and antenna output logical port antenna port has port matrix has a size of 4 by 1. Why exactly do we need precoding now? So by choosing the right weight for this precoding matrix, the UE can actually focus, the network can focus the energy towards the correct UE. So this aids in beamforming gain. It also creates a spatial separation between the layers of the channel so that the UE can untangle them at the receiver. And also null interference can be generated towards intended direction. Now but how are the weights of this precoding matrix determined? How does the GNODB knows which matrix, which precoding matrix to use? How does the UE knows which precoding matrix to use for decoding? What happens is the UE measures the channel and tells the GNODB as to which precoding matrix to use. But how can we transmit such a big precoding matrix that takes many bits for transmission over the channel every time the UE measures the channel and there is something different about it? Therefore, 3GPP has defined a codebook, which is a predefined set of weight matrices. The UE just sends a precoding matrix indicator or a PMI as a few bits. So both the UE and the GNODB shares the same codebook as is defined in 3GPP. So there are two kinds of codebooks actually. If you look here, there is type 1 codebook and type 2 codebook. Type 1 codebooks are usually used for single user MIMO, whereas type 2 codebooks are used for multi-user MIMO, and it has like around 20 plus bits of feedback, whereas type 1 codebook has like around 4 to 8 bits of codebook. Now the feedback loop in which the UE tells the G node B as to which precoding matrix indicator to use is as follows. Firstly, so we have the G node B here, and then we have the UE here. The G node B sends CSI-RS, which is channel state inference reference signals, on its logical port. The UE receives it, then the UE estimates the channel from the CSI-RS, and then the UE searches the codebook type 1 or type 2, then it finds the best precoding matrix, and it reports the PMI. It reports the PMI in it. Reports the PMI plus the rank indicator plus the channel quality indicator in the feedback. Then the G node B applies that weights precoding matrix, and then the mapping is performed. Yeah. So after precoding, the code words, the transport block, which is further processed into code words in the physical layer channel, which is further mapped into layers multiplied by precoding matrices, are mapped to logical antenna ports. So take care of the word logical. So this does not correspond to any physical antenna port. This is just logical. This is a concept. So this is the most important concept that is actually to be understood. An antenna port is not a physical antenna. It is a logical entity defined by its reference signal. So what exactly is a logical antenna port? So in plain English, if two symbols in a code word experience the same channel, then that means that they are on the same antenna port. So in our factory analogy, think of these logical antenna ports as the labeled loading docks from where packages are shipped. In another analogy, think of these logical ports as a TV channel. So channel number 7 is not a physical cable, it's a logical cable. So you can receive channel number 7 through cable or satellite or internet, and then the content is the same regardless of the physical medium through which it is transmitted. Now there are also scenarios where different antenna ports experience the same channel characteristics. So in this case, the antenna ports are said to be quasi-co-located QCL. They are called as quasi-co-located QCL. Now, why does this abstraction matter at all? So this helps that let's say that a G node B has like around 64 physical antenna elements. So it might expose only 8 logical ports to the UE. So the G node B can upgrade from 64 to say 128 physical antennas without changing anything to the UE. And also different vendors can implement the physical antenna layout however they require. The UE only estimate the channel per logical port and not per physical antenna. Now there are 3 reference signals that defines the logical ports. They are the DMRS, the demodulation reference signals, the CSI-RS channel state inference reference signals, and SRS sounding reference signal. Let us look at these signals in a bit more detail. The demodulation reference signals is transmitted alongside PDSCH and push. In downlink, both DMRS for PDSCH and PDSCH are transmitted at the same logical port. Similarly, in uplink, DMRS for push and POSCH are transmitted in the same logical port. Since the DMRS is pre-coded, the UE does not need to know the precoding matrix or the physical antenna config. It just estimates the effective channel per DMRS and then uses this for decoding PDSCH and PUSCH. So the DMRS experiences the same precoding matrix as the data. So it experiences the same propagation channel, and it is much more it's easy for the UE to thus decode this PDSCH and PUSCH. Then now the next reference signal that we talked about is CSI-RS, or channel state information reference signal. CSI-RS is quite the opposite of DMRS. It is not pre-coded. It is sent per antenna port without precoding. So the UE can estimate the row channel and report PMI, channel quality indicator, and uh, rank by estimating the CSI-RS. So CSI-RS is sent by the G0B in downlink, and the UE estimates it and reports it in uplink. Sounding reference signals is to the uplink what CSI-RS is to the downlink. So this is an unprecoded reference signal on logical ports that lets the receiver see the full channel matrix. That was it about precoding. Now, so this is where we cross from the logical world to the physical world. So in our factory analogy, think of these physical antennas as the actual trucks that deliver data. This is the actual medium. So by analog beamforming, what we mean is that each logical port's signal is fed to multiple antenna elements, each with a phase shifter. So by adjusting the phase, the signal from all the elements add up constructively in one direction and then destructively in other. So this creates a focus beam. So hybrid beamforming means that, so actually in practice, almost all the G0Bs use hybrid beamforming. So this is basically a combination of digital precoding and then analog beamforming. So this is exactly how massive MIMO works. So massive MIMO just means that the number of the transmit and receive antennas is quite huge. Let's just consider a massive MIMO panel with 64 transmit antennas and 64 receive antennas, and so this is just a sample mapping of the massive MIMO physical antennas to CSI-RS ports and DMRS ports and number of layers. This is just a sample mapping. Now that we have covered each of the components one by one, let us again reinforce the complete chain in complete RAN processing chain. So let's say that that MAC delivers one transport block to 5. So the transport block size is determined by the modulation coding scheme, the number of PRBs, and the rank of the channel. This is mapped by the 5 layer to code words. And the transport blocks undergoes CRC checks and then LDPC encoding and then rate matching and scrambling and modulation to generate code word. This code word is again mapped to or split into layers. So this layers in the transmission chain depends upon the rank of the channel. Then these layers are mapped to antenna ports, logical antenna ports via this precoding matrix. So this precoding matrix or W is selected based upon the PMI indication from the UE based on whether it is using type 1 or type 2 codebook. Now each logical port thus carries a weighted sum of both layers plus DMRS. Then each logical port is mapped into physical elements via analog beamforming, and then they are transmitted over the air interface. So this is a sample example of how the entire RAN processing chain works, how the transport block is mapped into physical antennas. Yeah, that was a brief explanation about the RAN processing chain. I hope that by the end of this video you would have a clear and intuitive understanding of how the entire mapping process works and how different is layers to rank of a channel and why this mapping itself is required. I thank you for watching this video, and see you in the next video. Thank you. Bye.